In Chapter 16, our final chapter of this course, our main goal is to introduce two new types of integrals and talk about some theorems regarding those integrals. But before we even get into that, we need to introduce a new type of function. So let's review what types of functions we have so far. So we have our normal function from Calc 1 or even from college algebra. So something like y equals f of x, or x is a number, you plug it in, you get another number out. We also have our vector valued functions. This would be something like, we might make this a boldface x, denoting that's a vector, is r of t, where t is just a number. We plug that number in there, we get a vector out. Then we have our multivariable functions, or functions of 2 or 3 variables. Be something like f of xy or f of xyz, something like that, where we put in two different numbers, x and y, and we get another number out, a single number out. Now, one thing that we haven't really brought up too much here, there is a notation for functions in general. The notation of, you put the name of the function, we put a colon, then you put whatever our name for our domain is here. Usually this would be some, for what we're doing here would be something like r, or r to the n, or something like that. And then we put an arrow pointing to the range. Again, this is whatever set of number, or whatever set of objects we can plug into the function, and whatever set of objects we get out of the function. So here, for these particular cases, this would be f takes in numbers and spits out numbers. So just real numbers and spits out real numbers. If our domain for this function is actually smaller, we might put a different set here, but just in general here, we're just saying that, specifying that we're plugging in a single number and getting out a single number. For this one, I guess I'm calling it r, so I should put r, plugging in a single number, and I'm getting out a vector. But a vector we're kind of identifying with the idea of something in R2 or R3. Let's even just go ahead and put this as Rn, where we can let n be 2, 3, or even higher if we need it to be. This represents a vector in n-dimensional space. For this one, for what I've drawn here, this would be from R2 to R, meaning that it takes in two numbers, spits out one number. Again, we can even generalize this a little bit, and instead of saying R2, we could say Rn, where n could be 2, 3, or even higher. In general, we could actually look at functions of the form Rm to Rn. That would be the broadest that we would talk about in a calculus kind of situation. We're not going to really go in that broad of generality, especially since a lot of what we use to tackle those kind of things would involve some linear algebra. Really, derivatives in this broad general sense would be m by n matrices, if that means anything to you. But we're not really going to talk about that here. What we are going to talk about is a specific case of this. Something where instead of having two different numbers here, we instead go from Rn to Rn, where the n is being fixed. And we're only going to be looking, of course, for n equals 2 and 3. N equals 1, obviously, we've already handled. But here we're going to be talking about when it's in 2 dimensions or 3 dimensions. We are going to call something like that a vector field, because we're essentially going to take the idea behind our vector value functions, where we're identifying points in 2 or 3 dimensional space with a vector pointing from the origin to that point. So the outputs of what we're going to have here are going to be vectors when we plug in 2 or 3 numbers. So the way the book actually defines our vector fields, we actually go ahead and write them out in 2 dimensions as this, where a vector field on R2, meaning in 2-dimensional space, is a function. They're going to use boldface characters, usually capital Fs. Of course, in writing this down, I'm not going to be able to make it boldface as well as you might want it to. Well, if that becomes an issue, I might end up putting arrows over things just to specify what's going on. But the point is that we have a function that assigns to a point x, y in some region in the plane. So this doesn't have to be over everything, but it's taking points in R2 and it spits out a 2-dimensional vector. For 3 dimensions, we really just change all the 2's to 3's. We're talking about a vector field on R3, a vector field on space, is a function f that takes a point x, y, z in whatever region of space that we're talking about to a 3-dimensional vector. Since vectors can be written in components and vector-valued functions can be written in components, we also take our vector fields and break them into components as well. A 2-dimensional vector field, so if we have f of x, y, taking in x and y and spitting out a vector, we can write this in components as something like p of x, y times I, so I here being the vector 1, 0, and then q x, y times j, where j is 0, 1. Or you could actually just write this as f equals pi plus qj. Basically, a lot of times it's easier to work with these p and q, which are really just functions of 2 variables, spitting out a single number. We have 2 functions, so that it's spitting out a vector, where those 2 numbers are the 2 components. Sometimes it's a lot easier to do that, and it also allows us a convenient way of using what we know about multivariable functions in order to work with these new vector fields. For 3 dimensions, of course, we would have 3 functions. We'd have a p of x, y, z times I. We have a q x, y, z times j. And the next one would be r times k. Or simply f equals pi plus qj plus rk. Now, using p, q, and r here is not necessary. We could actually use different notation here if we want to. We are going to make use of these particular names for these functions in some later sections, especially when we get to things like Green's theorem or stuff like that. So we'll kind of stick with this notation going forward. But do be aware that if we are working with multiple vector fields, we might do something instead where we say f is f1 times I plus f2 times j plus f3 times k, where instead of picking a new letter or picking new letters for our functions, we just use the same letter. Usually this f would be a boldface f, where each of these would be not bold, and then we just use numbers to denote which one of the components we're talking about. So that's just kind of some common notations, though there's not really anything completely standardized here. Now, the easiest way to get an idea of what a vector field is to actually kind of take a look at a picture. Unfortunately, GeoGebra does not have a vector field command, so I'm going to have to use a little bit of trickery to actually show what's going on here. But let's take a look at a particular example. I'm actually taking this from problem 4 in the book, So here we're going to say f of xy is equal to y times I plus x minus y, or sorry, x plus y times j. So our component functions here are y and x plus y. You could call that p and that q if you want to. So I go in here. I'm going to go ahead and define my first one. I'm actually wrote it as f1. If you want, we could call this p. I'm going to, since our first component was y, I'm going to put y in there. Oops, did not mean to delete that. Our second component was x plus y, so that's going to be my f2. Now I don't have anything drawn in here, is because I don't really have an easy way of actually graphing the vector field right away. What we could do is we could go ahead and just plot some vectors. So using our vector, we have some starting point, let's say 1, 2, and then we need to modify that vector by adding in our components. So we could actually say we're going from the point 1, 2 to the point 1, 2 plus what we get by plugging in 1 and 2 in for x and y. So when we plug in 1, 2 into f1, we get a 2, because that's the value of y. But for f2, we have to add 1 and 2 together, and we get 3. So what this is saying is that our vector field at the point 1, 2 gives this vector here point out in this direction. And we essentially do that for a bunch of different points in the plane. Essentially, we usually take a full grid of points and we attach a vector at each one of those points. Now what I'm going to do is use the sequence command, and actually stacking two sequences together, and this basically allows me to take those vectors that I just wrote out like I did there, but I'm giving it two different inputs, an x and a y value, and I'm letting those x and y values vary specifically from -10 to 10. I just chose that arbitrarily, but that means that for every grid point in our plane, every like from -10, -10, all the way to 10, 10 in a full grid, I'm going to plot a vector for each one of those. So let me actually just show that. So here we have a full grid of vectors. At every single grid point, we have a vector coming off of it. Now, of course, with the way I've drawn it right here, it's very cluttered. There's a lot of stuff going on because our vectors are fairly long. So I've actually, if you notice here, I put a scale factor on the vectors. So I can actually shrink the size of those vectors so I can actually see them a little bit better. So the vectors are actually longer than what we've drawn here, but it's a little easier to see. And so we can kind of get an idea of what this vector field is doing by looking at these particular vectors. Of course, there's a lot more vectors at all the intermediate points. This is actually a continuous thing going over every point in the plane. But this at least is something that we can picture. Now, this picture may not be unfamiliar to you. These are the same kind of pictures that we might use for something like wind speed or currents in the ocean or something like that, where we're basically showing what direction and what speed or magnitude we have for every point in a whole region. So this is actually very useful for a lot of applications. One particular application that we can talk about right now is, let's talk about gravity. Let's say we have a large mass, probably the Earth. We'll say it has mass capital M. And then we have a much smaller object, and we'll even just say that's kind of at a point because it's small enough that we're not really caring about how big it is. But we'll say it has mass little m. If we kind of assume that the Earth itself is at the origin, or at least the center of the Earth is at the origin, then we can actually talk about the position of the little object using a vector. Basically, we take our, probably should move the m away. Let me put it outside here. We take the vector pointing from the center of our Earth to that point of the smaller object. We'll call that r. Usually we put this as a boldface, or maybe if you prefer, we could put an arrow over that. But I'm just going to use little r. The force of gravity on this object due to the Earth, we can write as F of r equals minus gmm, g here is a constant, divided by the magnitude of r cubed times r. Now you might, if you're familiar with the gravitational formula, and I'm assuming a lot of you are, you might be confused by the fact that there's a cube here. Really what we're doing here is we're canceling out the fact that r itself has a magnitude. We're basically saying that this is minus gmm over the magnitude of r squared times r over the magnitude of r. We're essentially saying here that the magnitude of the force is the constant g times the product of the two magnitudes divided by the distance between those two objects. And then we have the direction of that as the unit vector. We're taking the unit vector pointing from the Earth to that object, and we're saying that by the minus sign that the force is backwards along it. So the force of gravity is actually that way. Not outwards from the Earth, but towards the Earth. But we need that to be a unit vector so it doesn't actually modify the actual magnitude of the force. The magnitude of the force is this part here. But what we've essentially done here is we've given a formula for the force at any given point in three-dimensional space. If I move my mass to somewhere else in three-dimensional space, it's just going to still follow this same formula. This gives us a vector field over three-dimensional space, usually referred to as the gravitational field. And you might say it's the gravitational field of the Earth, though do note here that the little m is in it. If we have a different object, it would have a different force just because we'd have to modify the masses put into the formula. Though we could actually remove that and maybe talk about the gravitational field without the actual mass in it. That'd be more of an accelerational field. We could actually write this in components. We could actually say that little r is xyz. That means that the magnitude of r is the square root of x squared plus y squared plus z squared. If we put those in here, that means our function, well, basically we have the cube of this thing on the bottom. The r here is actually, we could write this out as x times I plus y times j plus z times k. And so we end up getting a minus gmm x over x squared plus y squared plus z squared to the 3/2 power. So this to the 1/2 power, but then we cube it to get a 3/2 power. That's times I. But then we have essentially the same form for the other ones, but instead of the x, we have a y for the second component. That's times j. And then finally, the same kind of thing, but with a z. and that's times k. So the component functions are a little less appealing than the actual formula that we wrote it out in terms of the law of gravitation, but it does allow us to actually maybe tackle this in some calculus setting a little bit easier than this formula here, depending on the situation. Some are easier to use in different cases than others. This is an example of a force field. And not a force field in the sense of kind of the science fiction force field of like a barrier or something like that. No. This is actually a force field is a vector field in three-dimensional space where the vectors themselves are representing forces that would be applied to objects in that field. Other examples of force fields would be electric field generated by an electrically charged object. So it exerts an electrically charged object will exert forces on other electrically charged objects around it. Or we could talk about magnetic fields. That would be a force generated by a magnet or a moving charged object on other objects that would be affected by it, and stuff like that. I'm not going to get more into that. If you want to learn more about that kind of stuff, take a course in physics. All this vector stuff is incredibly useful. All this vector field stuff is incredibly useful anytime you actually want to deal with electromagnetism. Maybe a little more relevant to us in this class is where do we actually get some vector fields? We've actually seen a type of vector field pop up back in chapter 14. Recall when we had a function of 2 or 3 variables, something like f of xy or f of xyz, we had something that we called the gradient of the functions. So the gradient of f at a point xy is the derivative of f with respect to x times I plus the derivative of f with respect to y times j. Or if we were working in 3 variables, we end up with 3 components, of course, because we have 3 different partial derivatives. And so we have the gradient at any given point. But back then, we just viewed these as being essentially derivatives at single points. But really, they're examples of vector fields. If we start with this function, we end up having a collection of vectors at every given point that tell us something about the original function. If we start with a vector field f, and we want to identify a scalar function little f, something like this, where capital F is the gradient of little f, then we say little f is a potential function. A potential function for capital F. Technically, there are multiple potential functions if it does have a potential function, just because derivatives get rid of any constants. We could take little f and we can add a number to it and it will not change its gradient. But basically, once we have a potential function, we know all the possible potential functions. These potential functions are actually pretty useful for applications. For example, if we look at the function f of xyz is equal to capital G m over the square root of x squared plus y squared plus z squared. This is actually a potential function for the gravitational field that we looked at before. If we differentiate that with respect to x, we actually get this here. And then, of course, the same thing happens for x and y, or sorry, for y and z. So this is a potential function for gravity, or a gravitational field. And the very fact that we even have a potential function for gravity has some interesting implications that we'll talk about in another section. But the point here is that not every vector field does have a potential field, or a potential function. So if I give you a capital F, there may not be a little f that satisfies this condition. Essentially, you can kind of say that not every function has an antiderivative in this sense. Since if we want to think about the gradient as a derivative of the function. Not every vector field is actually a gradient of something. If it is, if there is a potential function, we say that capital F is let me put this a little bit clearer. Conservative. And conservative vector fields tend to be a lot easier to work with than non-conservative vector fields. But of course, we can't ignore the non-conservative ones. Identifying whether or not a given vector field is conservative can be a little bit tricky, and we're going to come back to that question in some later sections as well. So for the moment, we'll mostly use this idea of the gradient to actually generate some vector fields that we can actually take a look at, but we're not going to really identify whether or not a given vector field is actually conservative yet. So let's take a look at some examples. So we have here problems 25 and 26. These give us a function of two variables, and they ask us to find the gradient vector field of these two functions. And we'll go ahead and actually draw them as well. So let's just start with 25. So here we're taking this function and we want to find its gradient. The gradient involves taking the derivatives of the function. So what is f sub x? When we differentiate this, we're basically going to use the chain rule. We take the 2 down. That cancels out the 1/2. What's left is an x minus y. Technically, we're multiplying by the derivative of the inside with respect to x, but the derivative of x minus y with respect to x is 1. So f sub x is x minus y. F sub y, do kind of the same thing. In fact, the first step doesn't really change anything. We still cancel out the 1/2 with the 2 that we bring down. We still have the x minus y, but now we take that times the derivative of the stuff inside. Derivative of x minus y with respect to y this time is negative 1. So it's actually negative x minus y. So our gradient here, gradient of f, the first component is x minus y. Second component, I'm going to write this as y minus x. So that is our gradient. And that's really all we have to do for that first part. If we want to sketch it, however, we're going to change our functions here, kind of keeping the same setup that we had before. We have x minus y, and it plotted the one where the second component is 0, but I need to change the second component to y minus x. And we get this vector field here. So at every point, we have the vector pointing away from that point by whatever magnitude we have, and we kind of get an idea of what is going on. So one thing we can kind of tell already is that everything's kind of pointing away from the line y equals x. So the y equals x in here, all of those actually, if you can kind of see them, there's little dots along that line. That's because what we're graphing there is a vector with 0 magnitude, because if x equals y, both of these turn out to be 0. So technically we have a lot of small vectors in the middle, but then as we move away from that line, we get longer and longer vectors. Now recall that what the gradient means is for a function is that it always points in the direction of the greatest change, and the magnitude of that vector is how much it is changing. So when we say this is pointing away from the line y equals x, that means that our function is increasing away from that line. As we get further and further away, it's actually getting steeper and steeper. We're increasing faster the further away from that line we are. And it's actually not increasing at all on the line y equals x. So we can kind of predict here that maybe if we were to graph the surface, we would actually have kind of a U shape where it bottoms out down here on this line and then gets steeper and steeper away on the two sides. In fact, we can easily graph that since we can plot that in 3 dimensions. Remember, our original function, f of x, y, was 1/2 x minus y squared. And we have exactly what we expected, a kind of a U-shaped curve, and it's actually even a parabola because we have the square there. Though maybe that was not as easy to tell from our actual vector field here. On 26, this actually looks pretty similar to 25. In fact, if you're more of a beginning student, you might think, well, we can take that square and distribute it to both the x and the y. It kind of looks like that's what is happening there. But we'll see how that might actually change our result. Let's look at the derivative of f with respect to x. So in this time, we have a 1/2 x squared. When we differentiate that with respect to x, we get, well, 1/2 times 2x, or just x. The 1/2 times minus y squared is nothing, because it doesn't depend on x at all. So f sub x is just x. F sub y, for very much the same reason, the 1/2 x squared goes away. Then minus 1/2 y squared becomes a negative y. So our gradient is x comma negative y. Now if we go ahead and modify what we have in here, so our first one was, didn't want to delete it again. First one was just x. Our second one was negative y. And we now get a very different vector field than we had before for our other example. And in fact, the line y equals x does not really even come into play here. You can't really even tell that it has any significance to this particular surface. But what we can actually look at is what's going on with this vector field. You can kind of tell that all the vectors along the y-axis are pointing towards the origin. All the vectors along the x-axis are pointing away from the origin. And all the other vectors are kind of curving around, kind of sticking with the idea that we're moving towards the origin along the y-axis, but then as we get closer to the origin, they kind of start moving along the x-axis instead. And they kind of all do that. So you can kind of tell that along the y-axis, and since everything is increasing towards the origin is actually a high point for the y-axis. And along the x-axis, since everything's pointing away, the origin is actually a low point because everything's increasing from there. And so you can already kind of tell here that the origin is actually a saddle point for this particular surface. We can kind of get all that information from what we have drawn here in our vector field, as long as we know what to look for. So if we go ahead and modify this, so our new function looks something like this. In fact, this is our kind of our stereotypical saddle surface. I guess with maybe our stereotypical one would be x squared minus y squared without the 1/2, but the 1/2 is really only just modifying it. It's kind of shrinking things down in the vertical direction. Let's look at one last example that is essentially the same question, but with a little bit more complicated a function. We have a natural logarithm here. We are still looking for the gradient vector field. They also want us to plot a contour map. We'll talk about that in a moment. And we'll kind of take a look at what the surface looks like as well. Now, of course, it's exactly the same starting point. We take the derivatives of our function with respect to x and y. This time we do need to use the chain rule here. So the derivative of the natural logarithm gives us the derivative of the inside divided by what's inside. So we end up with a 1 plus x squared plus 2y squared on the bottom. On the top, the derivative of 1 plus x squared plus 2y squared, with respect to x specifically, is 2x. Obviously, the 1 and the 2y squared don't really matter here. Derivative with respect to y is basically the same idea. We still have that same inside, so we still have the same thing on the bottom. This time the derivative of the 1 plus x squared plus 2y squared is with respect to y instead of x, so the derivative there is 4y. So you can say the gradient of f is this whole thing and then followed by this whole thing. Or if you prefer, we could actually pull out anything that we can. We can pull out the denominator. We can even pull out a 2. Say 2 over 1 plus x squared plus 2y squared times the vector where what we haven't pulled out of here was x, and what we didn't pull out of here was 2y. Now, that's not going to help us graph this because we are going to have to plot this in terms of the component functions, because that's the way I actually have this set up. So my first component function, remember, was 2x divided by 1 plus x squared plus 2y squared. My second component was 4y divided by 1 plus x squared plus 2y squared. Doesn't look like much right now, but that's just because the actual gradient does not actually have as long of magnitudes as some of our previous examples. I'm going to need to increase the scale factor, and you can kind of see them get a little bit more prominent. And you can kind of tell we have some bigger vectors here near the origin, but they get smaller as we go out. But they're all actually pointing kind of away from the origin. Maybe not directly away, but they are pointing away. Now, they did want us to actually plot contour lines. Basically, what they're saying is we want the level curves. We're basically asking what happens if we set f of xy equal to a constant. And we plot various curves of just setting basically setting these equal to constants. So remember, our actual function here was ln of 1 plus x squared plus 2y squared. And we'll set this equal to various different numbers. So let's set it equal to 1 first. So the actual curve here is actually this curve here. And if you can't tell, it actually will turn out to be kind of an ellipse. If you solve this, you could turn it into the equation of an ellipse. If we plot this for other values, let's plot it for 2, for 3, 4, let's even go out to 5. So we've kind of gone out off of what I have plotted for the vector field, but we still got kind of an idea of what's going on here. We've got all these different level curves. These are just the various curves at which the original function, f of xy, is equal to these given values of the function. So at each point on this curve, that is where that function outputs 1. This is where that function outputs 5. So we can kind of get an idea of what the surface looks like from either of these. So the very fact that all of our vector field is pointing away from the origin is kind of giving us the idea that our function is increasing away from the origin. The origin is going to be a low point for this particular function. The contour curves also say the same thing. We get bigger values of the function are further away from the origin. And you can So these are kind of two different ways of tackling this particular function. One using vector fields, one using level curves. And whether or not one is easier than the other might depend on whether or not you can graph these level curves pretty easily, or whether or not you can take the derivatives very easily. Now you can go ahead and actually plot this. So remember, our original function was the natural logarithm of 1 plus x squared plus 2y squared. If we go ahead and put that in there, we have this surface here. So definitely has the origin as a low point, and it increases as you go out. Maybe you had kind of a picture of this where things might have been increasing faster further out. It might be a little bit surprising that it does kind of level off. But you can kind of tell that even from here by the fact that our contour lines are more bunched up closer to the origin than they are out here. They actually get further and further away. That means it's not increasing faster and faster as we go, but actually slower. Also, from our actual gradient vector field, you can see from the fact that the vectors get smaller as we go out. They are definitely increasing faster near the origin than they are out further away. So, just various ways of actually taking looks at functions of two variables using vector fields or level curves. Now, we're not going to go any more in detail in this particular section. This is kind of just introducing the idea of a vector field. We are going to be using that throughout this chapter, but we're going to start talking about integrals from this point on. We'll come back to vector fields specifically. I think in 16.5 we're going to be mostly talking about vector fields again, and we'll be talking about actual derivatives of those things. So I'll see you in the next video for line integrals.